So yesterday the model that we looked at for growth and decay, very simplistic model, just basically saying, well, it's going to be proportional to the population itself. In reality, we can extend it a little bit to take into account some other conditions, and I guess one of the most common problems that we look at is the heating or cooling down of objects. There's one thing we know for sure, that the temperature of the surroundings is like a barrier. If you take something out of the oven and you leave it on a bench top or whatever, well, the temperature will go down, but it can't go past the temperature of the room. Similar, if you take something out of the fridge and it's quite cold, well, it'll start warming up, but again, it can't go past the temperature of the room without external conditions being applied upon it. So for our graph, remember our graph it's an exponential. What that means for our graph is then, well, we're going to shift that horizontal asymptote of the graph. It's going to be like the barrier. So what happens then is our formula here becomes a constant, not just times p, but it's times p minus n, where n is some external condition. And the solution, well, there's a case that we don't normally consider. It's what's called the trivial case. I mean, if p was equal to a constant value of n, then, well, it's not changing. So the p to t would be 0, and n minus n is 0, so it satisfies the condition, technically. But that's not really the case we're interested in. We're interested in this one. So it's our exponential that we saw before, but it's shifted up or down depending on what those external conditions is, what that barrier to the problem is. So P still represents population, but the initial population will now be n plus a. Because if you make t equal to 0, again, the e to the kt will become 1, and we're left with n plus a. So the initial amount is n plus a. K, once again, is the growth or decay, depending on what we're looking at. And t is time. So here's one that comes from the 1993 paper. Again, the classic problem of temperature. So T is the temperature inside the room at time t. A is the constant outside air temperature. So that's going to be like our barrier in this case. So Newton's law of cooling states that the rate of change of temperature is proportional to T minus A. Show that. This is very similar to the other problems. We're going to show that this T is in fact a solution to our problem. So we'll do it the same way. Well, there's T. If I differentiate it, differentiate A, well, A is just a constant. That's going to be 0. Differentiate the CE to the KT, I get KCE to the KT. But we know T minus A, if I rearrange this, I get the T minus A is CE to the KT. So I could substitute that in, and there it is. It's satisfying our condition that our rate of change is equal to a constant times T minus A. So yes, it does satisfy our problem. All right, part B. So that outside air temperature is 5 degrees. And the heater breaks down. So it drops from 20 degrees to 17 degrees in half an hour. So how long is it going to take until that room temperature becomes 10 degrees? It's going to keep cooling down. Okay, so let's set it up. T is now going to equal 5. That horizontal asymptote, if you like, that barrier, the outside room temperature is 5 degrees. So we're going to have 5 plus CE to the KT. But our initial condition was the temperature was 20. So C must therefore be 15. So now I've got the formula to be 5 plus 15 e to the KT. Now we should be able to work out K using the information they've given us. They've told us after half an hour the temperature is 17. So if we sub that in and make K the subject, so move the 5 over, divide by the 15. To undo the exponential, we log both sides, and we get our constant is 2 log 12 over 15. That's the exact value, which I'll keep in my calculator. So now we want to know when is the temperature equal to 10 degrees. So when is 10 equal to 5 plus 15e to the KT? All right, so Again, subbing in, playing around with our exponential equation there. We get e to the kt is a third, log both sides. So t will be 1 divided by k, that value we've got stored, times the log of a third. So it comes out to be around about 2.46167. So almost 2.5 hours there. So I said, oh, well, about 2.5 hours. So again, I've rounded off, but I've made sure I've put the calculator answer out there so they can see, yeah, I did calculate it correctly. I'm saying, oh, well, about 2.5 hours. It'll drop to 10 degrees Celsius. Okay, well, that's really the only difference between what we did yesterday and what we did today, is that we're, if you like, shifting the graph up or down to that barrier, that external condition.